Hello everyone, I am Nireesha, working as assistant professor in EC department. In today's lecture, I would like to explain about the MOSFET. So before I start with the MOSFET, first I would like to give some of the differences between FET and BJT and MOSFET and FET. So FET stands for field effect transistor. It is a unipolar device. BJT stands for bipolar junction transistor and it is a bipolar device. So FETs are of two types, JFET and MOSFET. JFET stands for junction field effect transistor. MOSFET stands for metal oxide semiconductor field effect transistor. So this MOSFET is also known as IGFET, insulated gate field effect transistor. So again, the MOS transistors can be further classified into N-channel MOSFET and P-channel MOSFET. And each and every sub-classification of MOSFET have two different modes. So this N-channel MOSFET can be operated in two modes like enhancement mode and depletion mode MOSFET. And similarly, the P-channel MOSFET can also be operated under two modes. The first one is the enhancement mode and the next one is the depletion. So this slide is showing the differences, the basic difference between the BJT and the FET. So this BJT is a current control device, whereas the FET is a voltage control device. So that means the output current, the collector current is dependent on the base current I. So if you consider the field effect transistor, the output drain current depends on the input gate voltage. So here it is termed as VGS. So VGS is a control voltage. So this drain current depends on VGS. So here are some of the differences between MOSFET and the BJT. So the output current, as I just told you, the output current is controlled by the input gate voltage. And whereas in BJT, the collector current is controlled by input base current. Compared to MOSFET and BJT, so MOSFET is somewhat expensive compared to the BJT. And the switching speed and the frequency response of the MOSFET is somewhat better frequency response can be achieved using this MOSFET compared to the BJT. And coming to this thermal runaway point, when the MOSFETs heat up, the current flows through them decreases. They are less likely to be destroyed by overheat. So if you go to this point in the BJT, so when the bipolar transistors heat up, the gain increases, and so the current through them increases also. So this in case in turn causes further heating and at more gain and more current, this can cause a failure and this leads to thermal runaway. And the MOSFET have very high current gain, which is nearly constant for varying the drain currents. So lower current gain is possible or the lower current gain can be achieved in the BJT and which is not constant. So here are the sum of comparison points between JFET and MOSFET. The FETs can be operated in the depletion mode only. The JFETs can be operated only in the depletion mode. So whereas the MOSFETs can be operated either in depletion mode or in enhancement. And the MOSFETs have high input impedance, much higher than that of the JFETs. So this is due to negligible leakage current. Coming to the characteristic curves, JFETs have the characteristics curves more flat compared to the characteristics curve that we can achieve in the case of MOSFETs. When the JFET is operated with a reverse bias on the junction, the gate current is larger than it would be in a comparable MOSFET. So for the above reasons, the MOSFETs are somewhat easier in manufacturing compared to the JFET. And these MOSFETs are also widely used when compared to the JFET. So this is the tree diagram which is showing the different types of FET like JFET and MOSFET. And the JFET can be operated in two ways, like it have the two cases like P channel JFET and N channel JFET. And similarly, the MOSFET can also be have can also be used as a P channel MOSFET and N channel MOSFET. And in each FET, we have the depletion modes and enhancement modes. So metal oxide semiconductor field effector transistor. And coming to the terminals. So basically three terminals will be there: source, drain, and the gate terminal. Similar to the terminals which we have seen in the case of BJT. Some of the important points which are concerned to the MOSFETs are, so they are used in switching or amplifying controlling signals. And MOSFETs are voltage control device. So as we have seen it already, the drain current depends on the input gate voltage. So which we will call that voltage as control voltage. So the MOSFETs are voltage control devices. Uh, the three terminals will be there: source, drain, and gate terminals. And the MOSFETs have very high switching speed compared to the BJTs. And the classification depends on the mode, type of the mode, like enhancement mode and depletion mode. So this is the structure of the MOSFET. In this, we can observe the source terminal, drain terminal, and the gate terminal. The cross-sectional view of the MOSFET. We have a source, gate, and a drain terminal. So metal oxide semiconductor. So if you observe this cross-sectional view, the gate terminal is given with metallic contact. So after that, we have a silicon dioxide layer. Thick silicon dioxide layer will be there. So after that, the P-type substrate. So metal oxide semiconductor. So in between the source and drain terminals, we have a channel. The space between the source and drain terminals is called as a channel through which the charge carriers flow and which leads to the flow of current. So operating modes of the MOSFET we'll be discussing one by one. So these are the symbols of enhancement mode and depletion mode MOSFETs. The first one shows the symbol for N channel enhancement mode, P channel enhancement mode. So the right side symbols are depletion mode MOSFET symbols. First one is related to N channel. Second one is related to P channel. So the differences between N channel and P channel can be identified by the direction of the arrow direction. So by using this arrow direction, we can differentiate the symbols of enhancement mode, depletion mode, P channel and N channel type of MOSFETs. So coming to the operation of the MOSFET, so we just consider a MOSFET and we apply the gate to source voltage and we apply drain to source voltage. And already we know that the output drain current in a MOSFET is controlled by the gate to source voltage. So this controls the thickness of the channel. So based upon the thickness of the channel, the current conductivity depends. The current conductivity depends on the thickness of the channel. So if the gate to source voltage is given with the positive polarity, what happens? And similarly, the gate to source voltage is given with the negative polarity, what happens to the MOSFET we will see. So if you observe this first diagram, when the gate to source voltage is given with the positive terminals, so the gate terminal receives a positive charge and on the right side, we have the negative gated voltage diagram. If you give the negative potential to the gate terminal, so the gate terminal receives a negative polarity. So based upon this, the action of current happens. So this is the operation for N-channel MOSFET. So whenever we give the gate to source voltage is less than the threshold voltage. So threshold voltage is simply the minimum amount of voltage to turn on a particular device. So here the threshold voltage, some minimum amount of voltage will be required for the MOSFET to turn on. So this is called the threshold voltage. So whenever we apply VGS, which is less than the threshold voltage, so what happens to the channel? So there will be no inversion layer present under the surface. So if you increase the VGS voltage greater than the threshold voltage, then the channel exists or due to the formation of the inversion layer. And similarly, if you are not giving any kind of a drain to source voltage also, means that VDS is zero, then what happens? The depletion regions are symmetrical, right? A positive. A positive VDS means if you increase some little amount of VDS, what happens? The reverse biases, it reverse biases the drain junction, and hence the depletion region around the drain region will be widening more and more. And so the width of the depletion region also widens. Hence, no current flows even though we have applied VDS voltage which is greater than the zero. So as soon as we apply the VGS voltage which is greater than the threshold voltage, we receive only zero current. No current will be received because there is no conductivity in the channel between the source and drain regions. That we can observe in between the two diagrams shown below. So now let us see the other case. When this MOSFET is given with a voltage which is greater than the threshold voltage. And of course, we are applying little small amount of VDS also. With VGS greater than the threshold voltage, what happens? Conduction starts. The conductivity channel forms under a surface and it induces a transverse electric field also. Conductivity of the channel happens due to electric field, due to the induction of the electric field. So, because since we have applied the VGS voltage, which is greater than threshold voltage. So now slightly increase the drain to source voltage also. Then what happens? The conductivity presents, the conductivity starts and the current starts flowing. The charge carriers will move from source to drain region. So the drain current flows from through the drain tunnel. So that we can observe in the below diagrams. So if you increase more and more voltage to VDS, if you increase the higher voltages of the drain to source voltage, what happens? So at a point of this inversion layer, the density becomes very small at the drain end, and it is termed as a pinch off. So the value of VDS at which the pinch off voltage is denoted as VDS saturation. So this can be observed in the below diagrams. So this can be discussed later, soon after we complete this enhancement mode and depletion mode MOSFETs. We just come back to the slide. So coming to the MOSFET. So already we know that the MOSFET can be operated under two modes, enhancement mode and depletion mode. And we have seen the symbols also, schematic symbols also. So this is how the enhancement type MOSFET can be constructed. So basically, it will be off initially and no current flows between the source and drain terminals. The channel will be induced soon after we apply some positive voltage between the gate and source terminals. So coming to the construction, so how the enhancement mode MOSFET can be constructed. Two highly doped N regions are diffused into lightly doped P-type substrate. The source and drain regions are taken out through the small metallic contacts to N-doped regions. These N-doped regions are not connected via N-channel without any external voltage. So the gate terminal is connecting to P-doped substrate through a thin insulating layer of Si, silicon dioxide layer. And the channels are electrically induced in the MOSFETs when a positive gate source voltage is applied to it. VGS is applied to it. Coming to the operation. So similar kind of operation also do exist for the case of enhancement MOSFET also. So when the drain is applied with the positive voltage with respect to the source, no potential will be applied to the gate. Then what happens? A very small drain current, that is reverse leakage current, flows. So this enhancement MOSFET does not conduct when the gate to source voltage is zero. So it will be normally off initial. So when the gate is given with the positive voltage with respect to the source, then the charge carriers within the substrate attracts towards a positive polarity at the gate terminal and accumulate close to the surface of the substrate. So as soon as the gate voltage is increased, more and more electrons gets accumulated under the gate. Since these electrons cannot flow across the insulated layer, so they accumulate at the surface of the substrate just below the gate terminal. So this occurs and channel will be induced by forming an inversion layer in between the source and drain regions. So hence thereby the drain current starts flowing. At a particular value of VGS, there is a measurable current between drain and source. This value of VGS is called threshold voltage VT. For any voltage below VT, there is no channel. The strength of the drain current depends upon the channel resistance. In turn, depends on the number of charge carriers attracted to the positive gate. So finally, we have to observe in the case of enhancement mode MOSFET, the points to be noted are the channel does not exist initially with VGS is equal to 0. And conductivity of the channel is also enhanced by positive bias to the gate to source voltage. So this can be clearly depicted in this picture. So VGS is given with positive voltage, VDS is given with positive voltage, forming or inducing a channel in between the source and drain regions. So how the holes are getting repelled and how the electrons are getting attracted. We can observe in this diagram. So altogether, we can see the characteristics. So the enhancement mode MOSFET can be explained. The current, the drain current versus VGS and the drain current versus VDS can be explained by using the two characteristic curves, which is the first one is the drain characteristics and the transfer characteristics. So if you observe here, so whenever this VGS is going with the more positive voltages, the device becomes on and the drain current started flowing. So this drain current is controlled by VGS voltage. So as it is increasing more and more, the density of electrons in the induced channel increases. So hence thereby ID also getting increases. So the vertical portions of the curves are related to the ohmic region. And the flat shaped points are related to constant current region, or else we will call this region as saturation region. The current gets saturated, the drain current gets saturated and represented with the variable IDSS. So under the ohmic region, the MOSFET can be operated as voltage variable resistor. And in the saturation region, it can be used as a constant current source because wherever you find the current value, it remains constant at this particular region. So this transfer characteristic curve shows the drain current versus gate to source voltage. If you are moving with more positive values of PGS, so how the drain current is increasing? It is growing rapidly, it is increasing in this phenomena. And the equation related to the transfer characteristic curve is given in the slide. So ID is equal to K into VGS minus VT whole square. So therein we can get the formula for K also. It is a constant, of course. So the combinedly, the transfer characteristics and output characteristics, nothing but the drain characteristics are depicted over here. So this is the ohmic region. So under this ohmic region, the condition between VGS and the threshold voltage is that VGS is less than VT. So under the saturation region, almost the drain current remains constant. So next we have to come with depletion mode MOSFET. Depletion mode MOSFET characteristics can be obtained by applying negative gate voltage. All right. So with a negative gate voltage, the negative charges on the gate repels the conduction electrons from the channel, so leaving positive ions in their place. So thereby the N channel is depleted of the charge carriers electrons, thus decreasing the channel conductivity. The greater the negative voltage on the gate, greater is the depletion of N channel electrons. At sufficiently negative gate to source voltage, the channel is totally depleted and the drain current will be completely zero in this case. The symbol of depletion mode MOSFET you can observe here. So if you just observe the diagram, previous schematic diagram and the schematic diagram related to depletion type MOSFET, a conducting channel. So this conducting channel is already depicted over here. Means that conducting channel already exists. At the time of application itself, the channel will be created. So normally the device will be on with no bias. Means if you are not applying VGS also, the device already on. It is normally on since the channel already exists. So hence this depletion type MOSFET can be operated in two ways. Like it can be operated in depletion, I mean enhancement mode and also in depletion mode. Just the differentiating thing is a VGS voltage. If VGS is applied with positive voltage, it can be operated under enhancement mode. If VGS is operated under negative voltage, it can be operated under depletion mode. So the construction steps are quite similar. Coming to the operation. So when VGS is zero and the drain to source voltage is made with a positive, what happens? The electrons can flow between the source and drain even with the zero bias also. In this mode of operation, the gate terminal attracts the charge carriers from the p-type substrate to the N channel and reduces the channel resistance, which increases the drain current. When VGS is given with negative voltage, so this gate terminal repels some of the charge carriers, some of the negative charge carriers out of the channel and attracts the holes from the p-type substrate. This initiates a recombination of holes and electrons. This creates a depletion region in the channel and therefore reduces the number of free electrons in the channel. Increases the channel resistance also and reduces the drain current. The more the negative voltage on the gate, less the drain current. If you are going with more negative voltages of VGS, what happening here? The drain current will be reducing. So too much negative gate voltage can pinch off the channel. If you're going with the more negative values, the channel will be pinched off. Means the current values will be getting lesser and lesser. That can be observed in the characteristic curves. You just observe here. So when VGS is given with a negative voltage, the curves are lower. If you're going with the more positive values of VGS, the curves are becoming higher. They are going higher and higher. And you can also observe this mode of operation, depletion mode of operation. So VGS is given with a negative voltage and gate terminal is receiving the negative polarity to the metal. So inversion layer causes. This is the channel. The charge induced in the channel is this positive charge. And the transfer characteristics are similar to JFET only. And the equation of the drain current under transfer characteristics is given with this. ID is equal to IDSS into 1 minus VGS by VP whole square. So IDSS is a point of the current where we got the maximum value of the saturation value. So this is a pinch of voltage. So this pinch of voltage is actually the negative VGS voltage. So at this point of voltage, we have a least value of the drain current. So the current value is almost zero under this point of VGS. So this voltage is called the pinch of voltage. So we call this voltage as pinch of voltage. So finally, the conclusion or the differences between the depletion type and enhancement type. So we have seen the symbols for both N channel and P channel in the case of depletion type and enhancement type MOSFETs. Some points related to the channel. So already channel exists for depletion type. It exists permanently. So whereas for enhancement type, channel will be physically absent. So by applying the positive gate voltage, the channel will be induced, and based upon these voltage levels, the drain current variation will be observed. And coming to the mode of operation, depletion type MOSFET can be operated in both the modes, whereas enhancement type can be operated only in the enhancement mode. So the flow of current also can be observed by varying the VGS also. So practically no current flows on the application of the drain to source voltage. So the current flows only when VGS is above the threshold level in the case of enhancement type. So hope I covered maximum points related to enhancement type and depletion type of MOSFETs. And that's all for today's lecture. Thank you, everyone.